Hello and welcome to this clip going through the C3L6 2014 paper, first question. So the first important thing for you to point out is that this clip isn't meant to be a mark scheme. If you want to get hold of the mark scheme and the paper that goes with it, and the examiner's commentaries, you can go to www.c3l6.com. So like it says in the title, it is meant to be a challenge. And the information they give you on the front page of the paper, which we're looking at now, basically encourages you to try and be a bit deductive and problem solving in your approach. And with some careful reading of the question, it should be possible to attempt and access even what might first look like the harder parts. So it's also really important to lay out your calculations nice and clearly so the examiners can see what you're talking about. And don't forget to make sure that you use the appropriate number of significant figures and the correct units. So in terms of appropriate significant figures, what I'm talking about here is the least sensitive number of significant figures to which data is quoted in the question. So this should be your bare minimum. So for example, if the least sensitive number of significant figures is 3, I mean other parts of the question might quote to 4 or 5, but 3 therefore becomes your bare minimum. So that's your cue. When you look at the question that asks you to calculate, look for the least sensitive numbers in significant figures. So it's also important to use the actual relative atomic mass values provided in the periodic table that you get with the C3L6 paper. Don't be tempted to use values for elements that you've remembered from your A-level exam board's periodic table. So for example, if we look at chlorine, you'll see that its relative atomic mass is 35.45. In most A-level exam boards data sheets and periodic tables, it will be quoted as 35.5. So in your calculations, make sure that you use the values from this periodic table as opposed to values you might be recalling from elsewhere. So in every C3L6 question on every single paper, they start by giving you a bit of context and a bit of application perhaps that the chemistry you're about to be tested on is based. So it may also contain bits of information or pieces of data that you might need later on. So do have a skim through it first before you start so that you can put in your short-term memory what it contains and then come back to it later on if you need to. So the first part of question A talks about a mineral called bertrandite containing the elements beryllium, silicon, hydrogen and oxygen. So it asks you to consider the positions of the elements in the periodic table and predict what their oxidation number might be. So as with any oxidation number problem, you work on the assumption that if you've got a neutral compound, the sum of all the oxidation numbers in that compound will add up to 0. So an understanding of what oxidation number actually means is also important in this case. So oxidation number is the number of electrons an atom or ion of an element has involved in bonding in a molecule or compound. So hydrogen is in group 1, so it's an oxidation number of +1. Beryllium is in group 2, so is oxidation number +2. Oxygen is always -2 unless in a peroxide or bonded to fluorine, neither of which are true in this particular case, so it must be -2. So the final one to think about is silicon. So silicon is in group 4, but will it be +4 or -4 in this particular case? So the sum of the oxidation states must be 0. And also, in the presence of oxygen, all the other elements are less electronegative. So if this is the case, what will happen is they'll all assume positive oxidation numbers. So the most likely oxidation number for silicon will be +4. So now what we have to do is work out the value of x. We've got the empirical formula, so now we can apply the oxidation numbers that we've already deduced. So by taking the oxidation numbers we've already worked out, so if we remember that oxygen is -2 oxidation state, 8 + 2 + 8 = 2x. So therefore, x equals 9. So this next part looks at the extraction of the beryllium, including some purification of the bertrandite when it's dissolved in sulfuric acid. So it talks about extracting the aqueous layer with hydrocarbon solvent containing di-2-ethyl hexyl phosphoric acid, or DEHPA. So it says it's a diester, which means it's got two ester groups present in its molecule. So it's worth thinking about that before we go any further. So let's now have a go at these three structures. So the first structure is quite straightforward. I put in the numbering for the carbons to help you there. So in the second one, phosphoric V acid is phosphoric 5 acid, so phosphorus has an oxidation state of +5. Let's think about what di-2-ethyl hexyl phosphoric acid basically means. It means two of the OH groups we've just drawn in the structure for phosphoric 5 acid are replaced by 2-ethyl hexyl groups, as in two of them. So let's start with the bit that remains untouched. For it to be a diester, the oxygen from the OH has to be retained. So it's only the hydrogens which are actually replaced. So I've now added in red the 2-ethyl hexyl groups. Okay, moving on to part C, you'll notice that on the top right of the screen I've put some information that was on the previous page. And it talks about, on treatment with aqueous ammonium carbonate, most metal ions precipitate out, but the beryllium ions form ammonium beryllium carbonate, which is highly soluble in water. So after filtering it out, the solution left behind is heated to 95 degrees C, which causes a near quantitative precipitation of beryllium basic carbonate. And ammonia and carbon dioxide are also evolved. On heating further at 165 degrees C, it forms beryllium hydroxide. So I put the equations that I've been given on the left and right hand side of the arrow, and I also leave some space for the balancing numbers. And I'm also including some water as well, because there's quite a lot of oxygen on the left hand side that has to be used up. So let's start by adding up everything on both sides. And if we look carefully, the first one we can work with is beryllium. So there's one beryllium on the left hand side and 3 berylliums on the right hand side. So now we've got all the elements mismatched apart from beryllium. The next element we can deal with is nitrogen, by multiplying the ammonia on the right hand side by 12. So hydrogen is now increased to 38 on the right hand side. To balance it out, it makes sense to multiply the water times 5. So the final thing to do is to add 7, or rather to make up to 7 the number of CO2s, which balances everything out now. So in the second reaction, beryllium hydroxide is formed whilst heating in the presence of water, well actually steam at 165 degrees C. So I put down what I've got, and obviously not forgetting. So again I'm leaving spaces for my balancing numbers. So it's fairly straightforward, this one, nothing like the previous one. You can put in 3 BeOH2 on the right hand side. That now means there's 6 hydrogens on the right hand side, so there needs to be 6 on the left. And 2 CO2s on the right hand side balance the 2 carbonate ions on the left hand side. And just to point out, I put water in because the question said wet basic beryllium carbonate. So let's now move on to part D. So we're now into some calculation work. It's about enthalpy, so it's safe to assume that Hess's law or something similar will be involved somehow. So it says after further purification, the beryllium hydroxide is eventually converted into beryllium fluoride, and it gives the reaction with magnesium metal of that beryllium fluoride to give our elemental beryllium we're trying to get hold of, and a magnesium fluoride side product. So when they first start doing Hess's law work, what many people get confused about is which way around to draw the Hess's law diagram. The way to clarify this in your head is to look at the type of enthalpy data that you're given. So I've put the definition in that box there with the key parts of it in bold. And now we can build our enthalpy, our Hess's law diagram. So the elements I've put in the box are the constituent elements in their standard states as described in the definition. So now what we can do is we can populate that diagram with the correct numbers. So our indirect reaction route that we're going to follow is the red dotted line. So if you follow the red dotted line, you'll see that you go against the direction of the minus 1010, hence why it's positive 1010 in the calculation. It goes with the direction of the minus 1124, so that retains its negative sign, so that gives you 114 kilojoules per mole to the minus 1. So this section starts to get a bit more difficult. It's not just because we're looking at aspects of chemistry that are outside the A-level curriculum, but it's also the fact that it brings in your ability to visualize three-dimensional structures in your mind, and also pull in stuff like Pythagoras' theorem, which I've put in a little box there just to remind you. So the first part of part E asks you to calculate their molar volumes. The information it gives you is the density. So if we put the information into a table that we're given, the table itself might give us a clue as to how to work our way through this. So if you've got the number of grams in 1 centimetre cubed, you can work out the number of moles in 1 centimetre cubed. So to convert grams per centimetre cubed into moles per centimetre cubed, you simply take the grams per centimetre cubed as if it was a mass and you divide it by the molar mass, or the relative atomic mass, of each element. So doing that calculation in each case, using the values from the periodic table that the paper provided us with, we get 0.039 and 0.0205. Both of them are to three significant figures because the data we're given is to three significant figures. So to find the molar volume, what you need to do is 1 over density in moles per centimetre to the minus 3, and then multiply that by 10 to the minus 6 to factor in the difference between 1 metre cubed and 1 centimetre cubed. So that roughly gets these answers. So just in case you're following this with the mark scheme, the values I've got there might be slightly different because they use a slightly different method on the mark scheme. But I used three significant figures when calculating density in moles per centimetre to the minus 3, so that would have followed through in the calculation. So using the values that we've just calculated, it says in the second part of part E, given that beryllium and calcium have exactly the same packing efficiencies, in other words the fraction of the structure occupied by atoms, calculate the ratio of their atomic radii. So the way to work this out is to take the idea of 1 mole of atoms occupying a volume, and therefore if you've got the atomic radius equal to 1 atom, so if you imagine cubing the atomic radius is a bit like proportional to the volume of the atom, or the volume of a number of atoms, it could be proportional to the volume occupied by 1 mole of atoms. So taking this logic that the atomic radius cubed is proportional to molar volume, then if you want the atomic radius cubed over the atomic radius of beryllium, so the atomic radius cubed of calcium over the atomic radius cubed of beryllium, you need to do 1 over the molar volume of calcium divided by the molar volume of beryllium, because the molar volume unit is meters cubed per mole to the minus 1. So in order to find the ratio of the two atomic radii, you've got to cube root that, hence why the cube root's been put in now, and that gives you 1.738749433, which to three significant figures is 1.74. So for part F, I thought I'd just slightly expand on the two diagrams and just introduce what a unit cell is. So the unit cell is a little bit like a repeating unit of the arrangement in 3 dimensions of the atoms in a lattice. So in this case they're talking about the metallic lattice of calcium. So the metallic lattice is created by sticking these cubes together in 3 dimensions. And you can see how the atomic radius we've just dealt with actually fits into that in diagram II. So it's important to have a look at what they're saying. So I've highlighted in blue the part that we really need to think about here. It says you've got a regular cube shown with the dark lines with edge length A, which I'm now highlighting with little arrows just so you can see what I'm talking about. Whereas the lighter coloured lines within the lattice represent atoms in direct contact, which you can see clearly in the second diagram on the right. So for this question, part I, you need to visualise how the corners of the black cube bisect the corner atoms. So you need to think about the cube that's actually drawn in black and think about the corner atoms and how much of them is within that cube. So what I'm going to do is put 2 little red lines in the bottom left-hand corner atom, and you can see that if you just look at the front face facing the screen, only a quarter of the atom is within that face. If we take this to 3 dimensions, so in the cube, only 1/8 of the corner atom is included within the volume of the cube. So if we take that idea, multiply it by 8 because there's 8 corner atoms, that means 1 whole atom out of the 8 corner atoms is within the volume of the cube. So in each face there is half an atom within the cube. I've tried to illustrate this by having arrows point to each of these atoms that sit within the middle of the face. So there's 6 faces in your cube, so this accounts for 6 times a half equals 3 whole atoms. So that makes it 4 atoms in total within the cube. So they want us to find an expression for A. And if you look, I've put a little triangle in red, and the triangle happens to be right angled. So therefore what we can do is get this by Pythagoras' theorem. So let's call the hypotenuse of the triangle B. So according to Pythagoras' theorem, b squared should be equals to a squared. If we look at the hypotenuse of the triangle according to the second diagram on the right, you can see it's also 4r. So that now means that, going along with Pythagoras' theorem again, 2a squared equals 16r squared. So a squared must be equal to 8r squared. So a must be square root of 8 times r, equals 2.828427125r, which is the same as 2 root 2 times r. So the volume of the cube is simply a cubed, which gives us 22.627417 r cubed. So for F part 3, we already know that 1.55 grams of calcium equals 1 centimetre cubed of the lattice. So what we need to do is work out how many atoms are present in 1 centimetre cubed of the lattice. So we're not including the spaces between the atoms, of course. So we take the molar mass, times that by Avogadro's constant to get the atoms per centimetre cubed, and multiply that by 10 to the power of 6 to get the atoms per metre cubed, because there's 1 million centimetres cubed in 1 metre cubed. We also know that there's 4 atoms within 1 cube, because we worked that out earlier. So the cube is the unit cell, remember. So going back to the earlier part of the question, we know that within those four atoms we've got 22.627147 R3 meters cubed. So by taking the inverse of the number of atoms per meter cubed multiplying by 4, because there's 4 atoms in one unit cell, we can work out and isolate what R cubed is. So by taking 1.7175732 times 10 to the minus 28 and dividing it by 22.627147, which gives us that number for R cubed, which allows us to isolate the atomic radius. So this section of the question looks at the idea of metallic molecules, which is a little bit strange in an A-level sense because we're sort of used to dealing with metallic lattices in normal circumstances, standard conditions, with positive ions surrounded by a delocalized electron cloud. So what happens at extremely high temperatures is that some metals start to form alternative structures. Some even form diatomic molecules. In the same way that hydrogen does. Hydrogen is a group 1 element, just like lithium, for example. But this requires huge amounts of energy, so we don't normally see it. But the processes can be dealt with using normal thermodynamic calculations, such as those involving Hess's law. So once you get your head past the strangeness of what they're describing, the actual mathematics of what we're about to do isn't that hard. Perhaps an easier way of visualizing it is that the formation of metallic lattices is very thermodynamically favorable. In other words, exothermic, a lot of energy is released, so the structure is stabilized. So, in part G, you're asked to again calculate an enthalpy change. So the reaction that you're asked to calculate it for is given. So it's one thing thinking about breaking bonds, it's another thing remembering what the meaning of a bond enthalpy is. So it's worth having a think about that before we go any further. So in order to construct our Hess cycle, we need to have lithium bonds broken, as in the Li bond broken in gaseous conditions. So using the numbers that were given in the question, we can construct a Hess cycle that looks a little bit like that. So you can see that 2 moles of lithium gas is formed, but only 1 lithium-lithium bond is broken in gaseous conditions. So putting the numbers in and following the dotted line to represent the indirect route like we did before, that gives us minus 170.1 kilojoules per mole to the minus 1. So what they're asking you to do is to consider the removal of an electron from a molecule of lithium gas to leave a Li2 plus ion and 1 electron. So what you need to do is to tick the increase or decrease. So essentially you're comparing those two species in terms of bond dissociation enthalpy and bond length. So once the electron has been lost, the remaining cation, your Li2+, will be more attracted to those electrons which remain, including the bond pair. There's also another factor to think about. This cation, in its entity, is a molecule. So therefore a molecule has a bond, and a bond means the attraction for the bonding electrons of both of the nuclei, the positive nuclei. So let me try and illustrate what I've just said in terms of the Li atom now carrying the positive charge will tend to be repelled by the positive nucleus of the other uncharged lithium atom. So in the Li2 plus species, you have 2 lithiums, one of which is positively charged. So the ion that's still within the molecule on the right hand side, bottom right of the screen, has a greater positive charge, so it's repelled by the positive nucleus of the other atom. So as such, it takes less energy to break the bond, and the repulsion increases the bond length between the lithium atom and the lithium ion. So this final bit reconnects with the earlier application of beryllium in space travel, and it's modelled on the question we've just done, question H and G, with some enthalpy work and predicting and deducing. So G and H prepared you really for doing this particular question. So you're asked to construct a Hess cycle like before, but this time you're not given the equation, so you have to think about what it might look like. So we've been presented with a number of species. So Be2 as a gas is introduced as diberyllium. And later on in the same sentence they talk about the bond association and enthalpy and bond length change if one electron is removed from the molecule. So the next thing to be introduced is beryllium atoms, because they're talking about in part I, as in part I, the first ionization energy of beryllium atoms is 899.5 kilojoules per mole to the -1. So if it's the first ionization, it has to be in gaseous form, so that's why we put Be with gas. And obviously you'd have Be plus in gaseous form left over if your gaseous beryllium atom was to lose an electron during its first ionization. So that allows us to write out an equation for the bond dissociation enthalpy of Be2+. Notice there's no electrons lost yet, because all we're doing is breaking the bond between Be plus and Be, just like we did with lithium before. So section H, completion, that allowed us to have a think about this one and have a little bit of prior knowledge about what might be going on. But there's a slight hitch. We're only given the data for Be2, not Be2+. So what we have to do is alter our Hess cycle a little bit. So by putting in all the things that were given, you can start to see how they interconnect. Now, this allows us to work out the value for delta RH in a similar way to before. So that gives us 193.5 kilojoule per mole to the -1. So then it says, in light of your answer to part I, or part 1 rather, predict how the bond length will change as an electron was removed from the Be2 gas molecule to form the Be2 plus gas ion. So in this case, the enthalpy change is endothermic, has a positive sign as opposed to a negative sign. So the attraction between the positive beryllium species and the bond electrons is stronger. So if we draw out the molecule in the same way that we did for Li2+, and we think about the positivity of the nucleus, beryllium has more protons than lithium, which could justify the fact that its bond dissociation enthalpy is 193.5, a positive value. So if you get a more endothermic bond dissociation, this will equal a stronger attraction between beryllium and beryllium plus in the molecule that's been drawn, which will lead to a decrease in the bond length this time round. Okay, so that takes us to the end of this question and the end of this clip. Thanks a lot for sticking with it. It was a slightly longer one this time because the question is a bit more difficult than average. But until next time, I'll see you soon.